Hi, this is Tim Shue from San Jose State University. I'm here today to talk about logarithmic functions. So we'll start about talking about the definition of the log of x to the base a. We'll look at certain key global properties of logarithm functions. We'll look at algebraic properties of the log of x to the base a. And we'll finish by looking at a few special log functions of particular use. Okay, so what is the definition of the log? Well, let's fix a base a greater than 0. And at this point, you should know all about a to the x, the exponential function with base a. So go back and review that material if you haven't already. In particular, it should sound like a kind of familiar thing to you that a to the x is a one-to-one function. If it isn't, you can safely accept that this is true without worrying about it too much, since we didn't really explain to you anyway. We'll talk. And so, knowing that a to the x is the exponential function is one-to-one, that means it has an inverse, and so we can define the logarithm function with base a, written log of x to the base a. So this symbol here is pronounced log of x to the base a. That is defined to be the inverse function of a to the x. And if that sounds like total nonsense to you, go back and review inverse functions, or maybe really just check out the next example, which should jog your memory if you've at least seen this sometime before. Okay, so to look at a concrete example, which I hope will illuminate the definition, let's figure out what is the log of 128 to the base 2. Well, answer, since log to the base 2 is the inverse function of f of x equals 2 to the x, the value of log of 128 to the base 2 is equal to the input to f of x, the forward function, that produces the output 128. That is, the log of the value of the inverse function at 128 is the input to the forward function that produces the output 128. In other words, the log of 128 to the base 2 is the solution to 2 to the equals 128. And after some trial and error, you might eventually see that 2 to the 7th is 128. And so, as reviewed, I want to freeze the video right here and see if you can figure out what that tells you about the log of 128 base 2. Well, hopefully you figured out that the log of 128 to the base 2 is equal to 7. Okay, so now turning to certain key global properties of the log function, we see that, let me remind you that the plot of 2 to the x, the graph of 2 to the x looks like this. And so it turns out that the inverse function of 2 to the x, or the log to the base 2, can be written as the natural log of x over the natural log of 2. This is a special case of what is known as the change of base formula, but I'm happy if you just take my word for it. Anyway, so taking any a greater than 1, and let me remind you that here are some of the key characteristics of the graph of a to the x, here, which is over here in green. So the graph is increasing and concave up. It's a smiley face. And the domain of it is all real values of x, so you can plug in whatever you want for any real value of x, and what you get as an output is some positive y. The y-intercept is y equals 1, and there's no x-intercept, and as x goes to minus infinity out this way, y goes to 0. So if you remember just general nonsense about inverse functions, that means that if you look at the graph of the log of x to the base a for any a greater than 1, then we get that the graph of this function is increasing concave down. You get that by flipping it over the red line. The domain of this inverse function is all x greater than 0 because the range of the forward function was all y greater than 0, and the range of the inverse function is all real values of y because the domain of the forward function was all real values of x. The x-intercept of this inverse function, the log, is x equals 1, and there's no y-intercept. And finally, as x approaches 0, this is the trickiest one, as x approaches 0, y approaches negative infinity on the graph of the log of x to the base a. There. So anyway, so where these come from aside, it's really just enough that you sort of remember that these are the key aspects of the graph of the log of x to the base a. Okay, turning to the algebraic properties of the log of x to the base a. First of all, since the log of x to the base a is the inverse function of a to the x, we see that the log of a to the x to the base a is x, and a raised to the power of the log of x to the base a is equal to x, where the left-hand equation over here holds for all values of x, and the right-hand equation holds for all x greater than 0. In other words, just as with any inverse function, the log to the base a undoes exponentiation to the base a, and vice versa. Also, remember the laws of exponents from about 10 zillion years ago, and here they are. A to the x plus y equals a to the x times a to the y. A to the x minus y equals a to the x over a to the y. A to the x times r equals a to the x, all quantity raised to the rth power. and a to the 0 equals 1. And the thing that you can sort of use to remember these is that exponentiation makes simpler operations in the exponent become more complicated when you pull them outside. So addition becomes multiplication, subtraction becomes division, multiplication in the exponent becomes exponentiation. Well, each of those laws of exponents becomes an analogous law of logarithms. So if you remember, the sum in the exponent becomes multiplication. The log version of that is that the log to the base, okay, I'm going to stop saying log to the base a because it's all to the base a. Let me just say log. The log of a times b is equal to the log of a plus the log of b. Here, this difference law becomes the log of a over b is equal to the log of a minus the log of b. And this multiplication law up here becomes that the log of capital A raised to the power r is r times the log of capital A. And finally, the log of 1 is always equal to 0. And again, you can remember this by saying that logs make things simpler. The log of multiplication becomes an addition, the log of a division becomes a subtraction, and the log of a power becomes a multiplication. All right, now finally turning to some special log functions. Remember that the exponential function e to the x, where we take the base to be equals 2.718281828 and so on. That is the most important exponential function because of its properties in calculus. Well, correspondingly, its inverse, the natural log function, the natural log of x, which is an abbreviation for the log of x to the base e, is the most important log function because of its calculus function properties. I should also mention, for the sake of completeness, that the common log function, which is written log of x, unfortunately, it is the log of x to the base 10, and it's unfortunate because this is not really that useful for our purposes in calculus, but everybody else uses it in the real world, so we're kind of forced to use that notation. So that sometimes appears in applications because people write numbers in base 10. People are not wired for calculus for some strange reason. Anyway, since the log of x to the base 10 happens to be equal to the natural log of x over the natural log of 10, we can safely forget about common log for the purpose of calculus, because anything you would want to know about a common log, you can figure out using natural logs. Well, let's just forget about it. All right, enough of watching the math equivalent of a cat video, so go do something useful. Thanks, bye!